Hello there, and welcome to the Sleepy Library. It's lovely to have you here. Before we begin, I'd love to know, where in the world are you watching from tonight? A quiet bedroom somewhere in Asia? A sleepy living room in Europe? A cozy spot in the Americas? Or perhaps somewhere else entirely? Wherever you are, I hope you're comfortable, safe, and ready to gently explore something truly amazing. If you enjoy these relaxing explorations and would like to hear more, a like and subscribe really helps this sleepy little channel float along. And to those of you already subscribed, thank you. Truly, your support means more than you know. Tonight, we're going to talk about something happening right now, at this very moment, beneath your feet. Something so slow you'll never feel it, yet so powerful it shapes mountains, creates oceans, and rearranges entire continents. The ground you're standing on, sitting on, lying on, is moving. Not quickly, not dramatically, but it is moving. And it has been for hundreds of millions of years. So, settle in, close your eyes if you'd like, and let's begin a gentle journey through time and space. A journey about how continents move without us ever realizing it. The surface of our planet feels solid. When you walk on the ground, it doesn't shift beneath your feet. When you build a house, it stays where you put it. When you look at a map, the shapes of the continents seem permanent, unchanging, eternal. But that feeling of permanence is an illusion. A beautiful, comforting illusion created by the shortness of our human lifespans. Because the earth beneath us is not solid at all. At least, not in the way we think of solid. The ground is moving, constantly, in a slow and ancient dance that has been going on for billions of years. Every continent, every island, every piece of land you've ever stood on is riding along on massive slabs of rock called tectonic plates. And these plates are gliding, ever so slowly, across the surface of our planet. How slow, you might ask? Well, imagine watching your fingernails grow. That's about the speed we're talking about. Some tectonic plates move as slowly as 1 centimeter per year. Others move a bit faster, maybe 7 or 8 centimeters per year. To put that in perspective, that's about the same speed that your hair grows. Incredibly slow by human standards. Yet, over millions of years, this tiny movement adds up to something extraordinary. The entire surface of the Earth, the crust we live on, is broken into giant fragments. Think of it like a cracked eggshell. Except this eggshell is thousands of kilometers wide and floats on a layer of hot, partially melted rock beneath it. These fragments, these tectonic plates, are always moving, always shifting, always changing the face of our planet, 1 millimeter at a time. Right now, as you listen to these words, North America is moving away from Europe. Australia is creeping northward toward Asia. Africa is slowly pulling apart along a massive crack running through the eastern part of the continent. India is still pushing into the rest of Asia, causing the Himalayas to grow taller each year. All of this is happening right now, beneath our feet, invisible and unstoppable. But it wasn't always obvious that this was happening. For most of human history, people believed the continents were fixed in place, permanent features of the Earth that had always been exactly where they are now. After all, how could something as massive as a continent possibly move? The story of how we discovered continental movement begins in the early 1900s with a German scientist named Alfred Wegener. Wegener was a meteorologist, someone who studied weather, not a geologist. But he had a curious mind and sharp eyes, and one day, while looking at a map of the world, he noticed something interesting. The coastlines of South America and Africa looked like they could fit together, like two pieces of a puzzle. The bulge on the eastern side of South America seemed to match perfectly with the indent on the western side of Africa. It was as if, at some point in the distant past, these two continents had been connected and then somehow drifted apart. At first, it was just an observation, a curious coincidence. But Wegener kept thinking about it. He started looking for evidence, and what he found was remarkable. Fossils of the same ancient creatures were found on both sides of the Atlantic Ocean. Plants that had lived millions of years ago appeared in both South America and Africa. Rock formations on one continent matched perfectly with rock formations on another, as if they had once been part of the same geological structure. All of this evidence pointed to the same conclusion. The continents hadn't always been where they are now. At some point in Earth's history, they must have been connected. And then, somehow, they drifted apart. Wegener called his idea continental drift. In 1912, he presented his theory to the scientific community. He suggested that all of Earth's continents had once been joined together in a single massive landmass. He called this supercontinent Pangaea, a name that comes from ancient Greek words meaning all lands. Imagine that. 300 million years ago, there was no Atlantic Ocean, no separate continents, just one enormous landmass surrounded by a single vast ocean. If you had lived back then, you could have walked from what is now New York to what is now Morocco without ever getting your feet wet. You could have traveled from Antarctica to India on foot. All the land on Earth was connected, forming one giant continent. But Wegener's idea was controversial. Most scientists at the time didn't believe him. They couldn't accept that continents could move. How? They asked. What force could possibly push something as massive as a continent across the Earth? Wegener didn't have a good answer to that question. He suggested that perhaps the rotation of the Earth somehow pushed the continents around. But other scientists quickly showed that this couldn't work. The forces weren't strong enough. Without a mechanism, without a way to explain how continents could move, most scientists dismissed Wegener's idea. They thought it was interesting, perhaps, but ultimately wrong. Wegener spent years trying to convince people, but he never lived to see his theory accepted. He passed away in 1930 during an expedition in Greenland, his idea still rejected by most of the scientific community. It would take another 30 years before scientists finally understood that Wegener had been right all along. And the key to understanding came not from studying the land, but from studying the ocean floor. In the 1950s and 60s, scientists began mapping the bottom of the oceans using new technologies developed during the Second World War. What they discovered was astonishing. The ocean floor wasn't flat and featureless. Instead, it was covered with underwater mountain ranges, deep trenches, and strange magnetic patterns that seemed to tell a story. The most important discovery was something called seafloor spreading. Scientists found that in the middle of the Atlantic Ocean, there was a long underwater mountain ridge. And at the center of this ridge, hot molten rock was constantly bubbling up from deep inside the Earth. This molten rock, called magma, would cool and solidify, creating new ocean floor. As more and more magma pushed up, it would spread the ocean floor apart, like a conveyor belt moving in slow motion. This was the missing piece of the puzzle. This was how continents could move. They weren't pushing through the ocean floor like ships through water. Instead, the entire ocean floor was moving, carrying the continents along with it. The Earth's crust, both the continents and the ocean floors, was broken into these giant tectonic plates. And these plates were riding on a layer of hot, partially melted rock deep inside the earth. Think of it like this. Imagine a pot of thick soup on a stove. As the soup heats up from below, the hot liquid rises to the surface, spreads out, cools down, and then sinks back down to be heated again. This creates a circular motion, a convection current. The same thing happens inside the earth. Deep in the mantle, the layer beneath the crust, rock is so hot it can flow like a very thick liquid. Heat from Earth's core causes this rock to rise, spread out beneath the crust, cool down, and sink back down. And these convection currents, these slow circular motions of rock, are what drive the movement of tectonic plates. So, the plates aren't being pushed from the surface, they're being pulled and pushed from below by currents of hot rock moving through the mantle. It's like a giant, planetary-scale conveyor belt system, operating in slow motion, powered by the heat from Earth's core. With this understanding, Wegener's theory of continental drift transformed into what we now call plate tectonics. And suddenly, everything made sense. The matching coastlines, the similar fossils, the identical rock formations. They all fit together because the continents had once been together. Pangaea had been real. And over hundreds of millions of years, it had slowly broken apart, the pieces drifting to where they are today. Now let's travel back in time. Let's go back 335 million years ago, to a time when Pangaea was just beginning to form. The Earth looked very different then. There were already continents, but they were scattered across the globe, separated by ancient oceans with names we can barely pronounce. Gondwana, Euramerica, Siberia. These were the pieces that would eventually collide and merge to form Pangaea. The process took millions of years. Slowly, driven by the movement of tectonic plates, these landmasses drifted toward each other. When they collided, the impact was tremendous. Mountains rose up where the continents crashed together. The Appalachian Mountains in North America, the mountains of Scotland, the ranges in Morocco. All of these formed from the collisions that created Pangaea. They're all part of the same mountain-building event, now separated by oceans that didn't exist back then. By about 300 million years ago, Pangaea was fully formed. One supercontinent, stretching from pole to pole, surrounded by a single global ocean called Panthalassa. If you could have looked at Earth from space back then, you would have seen one side of the planet almost entirely covered by water, and the other side dominated by this massive C-shaped landmass. Life on Pangaea was strange and wonderful. This was during the time of the dinosaurs' ancestors, before the great reptiles ruled the Earth. The climate was extreme. The interior of Pangaea, far from any ocean, was a vast desert, one of the largest deserts in Earth's history. Without ocean breezes to bring moisture, the center of the continent baked under the sun. But along the coasts, life flourished. Forests grew, creatures evolved, and because all the land was connected, species could spread across the entire supercontinent. This is why we find fossils of the same creatures on continents that are now thousands of kilometers apart. The formation of Pangaea had profound effects on life on Earth. With all the continents joined together, there was much less coastline than there is today. Coastal environments, with their shallow seas and tide pools, are incredibly rich in biodiversity. When Pangaea formed, much of this coastal habitat disappeared, leading to what scientists call the Permian-Triassic extinction event, the largest mass extinction in Earth's history. About 96% of all marine species and 70% of all land species went extinct during this time. The cause of this massive extinction is complex, but the formation of Pangaea played a significant role. With less coastal habitat, marine life had fewer places to thrive. The interior of Pangaea was so dry and hot that vast areas became uninhabitable. Ocean circulation patterns changed, affecting climate and the distribution of nutrients in the sea. Some scientists also believe that massive volcanic eruptions, occurring as Pangaea was forming, released huge amounts of carbon dioxide and other gases into the atmosphere, causing rapid climate change that many species couldn't survive. But life is resilient. After the extinction event, new species evolved to fill the empty niches. In the seas, new types of fish and marine reptiles appeared. On land, the ancestors of dinosaurs began their rise to dominance. Insects diversified, including the evolution of some of the largest insects that ever lived. In the swampy coastal forests of Pangaea, dragonflies with wingspans of over 70 centimeters buzzed through the air. Millipede-like creatures, more than 2 meters long, crawled through the leaf litter. It was an alien world by our standards, but it was also the world that would give rise to the dinosaurs. The climate of Pangaea was marked by extremes. Along the coasts, where moisture from the ocean could reach, there were dense forests. These forests were different from today's forests. They were dominated by ferns, seed ferns, and early conifers. The flowering plants that dominate many ecosystems today hadn't evolved yet. The trees were giant tree ferns and primitive conifers, creating forests that would look strange to our eyes, but that supported a diverse community of insects, amphibians, and early reptiles. As you moved inland, the climate became progressively drier. There was a band of subtropical forests, then scrublands, and finally, in the heart of Pangaea, vast deserts. These deserts were unlike any that exist today because of their sheer size. They extended for thousands of kilometers, far from any ocean, receiving almost no rainfall. Daytime temperatures could reach extreme levels, while nights were cold. Only specially adapted organisms could survive in these harsh environments. Interestingly, the extreme continental climate of Pangaea may have driven important evolutionary adaptations. Reptiles, with their scaly skin and ability to lay eggs with hard shells, were better adapted to dry conditions than amphibians, which needed to stay moist and often laid their eggs in water. The harsh interior of Pangaea may have provided the selective pressure that led to the evolution of the first fully terrestrial vertebrates, creatures that could survive far from water. The unification of all the continents also allowed animals to spread across vast distances. Fossils of a small reptile called Mesosaurus have been found in both South America and Africa, in rocks that formed when these continents were part of Pangaea. This creature couldn't have crossed the modern Atlantic Ocean, but it didn't need to. The land was connected. Similarly, the plant Glossopteris, a seed fern, is found in fossil deposits across South America, Africa, India, Antarctica, and Australia, all places that were connected in the Gondwana portion of Pangaea. These fossil distributions were some of the key pieces of evidence that Alfred Wegener used to support his theory of continental drift. How else could the same species be found on continents now separated by vast oceans, unless those continents were once connected? The patterns made perfect sense when you reconstructed Pangaea, bringing all the continents back together. The world of Pangaea was also a world of seasonal extremes. The massive landmass created what scientists call a monsoon climate on a continental scale. During summer, the interior of Pangaea would heat up dramatically. This hot air would rise, creating a low-pressure zone that would draw in moist air from the ocean. The result would be intense seasonal rains along some coastal regions. During winter, the process reversed, creating dry conditions. These seasonal swings were far more extreme than anything we experience today. Imagine living in a place where it might not rain for 8 or 9 months of the year, and then suddenly experiencing torrential downpours for several months. This kind of climate would require special adaptations, and indeed, we see evidence of these adaptations in the fossil record. Many plants from this time had features that helped them survive long, dry periods, such as thick, waxy coatings on their leaves, or the ability to go dormant during droughts. But Pangaea didn't last forever. Nothing in geology does. After about 160 million years of existence, Pangaea began to break apart. The same forces that had brought it together, the convection currents in the mantle, now began to pull it apart. Cracks formed in the crust. Magma bubbled up through these cracks, creating volcanic rift zones. The landmass started to split. The breakup wasn't sudden. It was a gradual process that took tens of millions of years, beginning with small rifts that slowly widened into ocean basins. About 200 million years ago, during a time period we call the Triassic, the first major split occurred. A rift opened up, separating Pangaea into 2 large pieces. The northern piece, which included what would become North America, Europe, and Asia, was called Laurasia. The southern piece, which included what would become South America, Africa, India, Antarctica, and Australia, was called Gondwana. For a while, these 2 supercontinents existed side by side, separated by a growing ocean called the Tethys Sea. But the breaking didn't stop there. Over the next 150 million years, Laurasia and Gondwana continued to fragment. India broke away from Antarctica and began a long journey northward across what is now the Indian Ocean. Africa and South America split apart, creating the Atlantic Ocean between them. Australia separated from Antarctica and drifted north toward Asia. Antarctica moved south to the pole and became covered in ice. By about 65 million years ago, around the time the last dinosaurs went extinct, the continents were starting to look more familiar. They weren't quite in the positions they are today, but they were getting there. The Atlantic Ocean was still relatively narrow. India hadn't yet collided with Asia. Australia was still quite far south. But the basic arrangement, the general pattern, was beginning to emerge. And then came the collision that would reshape the face of the planet. About 50 million years ago, India, which had been drifting north for millions of years, finally crashed into the rest of Asia. This wasn't a quick collision. It was a slow, grinding impact that took millions of years. But the result was spectacular. The collision crumpled the crust, pushing rock upward to create the highest mountains on Earth. The Himalayas, the Tibetan Plateau, the vast mountain ranges of Central Asia. All of these formed from India's collision with Asia. And here's the remarkable thing. That collision is still happening. Right now, India is still pushing northward into Asia at a rate of about 5 centimeters per year. And because of that, the Himalayas are still growing, still being pushed higher, gaining about 5 millimeters in height each year. Think about that for a moment. The tallest mountains on Earth, mountains that seem eternal and unchanging, are actively growing right now. They're being pushed up by the slow, relentless pressure of India moving north. Every year, Mount Everest gets just a tiny bit taller. Not much, just a few millimeters. But over millions of years, those millimeters add up. This is the power of continental movement. Forces so gentle you can't feel them, yet strong enough to raise mountains, open oceans, and reshape entire continents. Now let's talk about what's happening right now, in our present day. The continents aren't finished moving. They're not sitting still, waiting for something to happen. They're in motion, right at this moment, continuing their ancient journey across the face of the Earth. Let's start with Australia. Of all the continents, Australia is moving the fastest. It's racing north toward Asia at a speed of about 7 centimeters per year. That might not sound like much, but in geological terms, it's incredibly fast. Over the past 20 years, Australia has moved about 1.8 meters north. That's enough to cause problems for GPS systems, which rely on knowing exactly where things are on the planet. In fact, Australia had to adjust its official geographic coordinates in 2016 to account for how far north it had moved. Where is Australia going? If it keeps moving at its current speed, it will eventually collide with Southeast Asia. This won't happen in our lifetimes, or in the lifetimes of our great-great-great-grandchildren. It will take millions of years. But eventually, barring any changes in plate motion, Australia will crash into the islands of Indonesia, Papua New Guinea, and the southern tip of Asia. When that happens, new mountains will rise, ocean basins will close. The map of Asia will be redrawn by the slow but inevitable force of tectonic movement. Scientists who study this process say it's not a question of if, but when. Whether we like it or not, one geologist said, the Australian continent is going to collide with Asia. It's written in the motion of the plates, in the direction of movement, in the forces driving the crust across the mantle. The story of Australia's movement is particularly fascinating because it shows us how fast geological processes can be, at least in relative terms. Australia separated from Antarctica about 80 million years ago, and for the last 50 million years, it's been steadily moving northward. During this time, it's traveled thousands of kilometers across the surface of the planet. If you could watch a time-lapse of Earth over the last 50 million years, you'd see Australia sliding across the Indian Ocean like a ship crossing a sea, leaving Antarctica behind at the South Pole and heading toward the tropical regions near the equator. This northward movement has had profound effects on Australia's climate and ecosystems. When Australia was connected to Antarctica, it had a much cooler, wetter climate. Rainforests covered much of the continent. But as Australia drifted north into warmer latitudes and became isolated from other landmasses, its climate became drier. The rainforests shrank and were replaced by the vast deserts and dry grasslands we see today. The movement of the continent literally changed the nature of life on it. The isolation of Australia also led to the evolution of its unique wildlife. When Australia separated from other continents, it took with it a population of marsupials, pouched mammals like kangaroos, koalas, and wombats. On other continents, marsupials were eventually outcompeted by placental mammals. But in Australia, isolated by ocean, marsupials flourished and evolved into the diverse and remarkable creatures we know today. Continental movement didn't just change the landscape, it shaped the evolution of life itself. Now, as Australia continues its journey north, scientists wonder what will happen when it finally meets Asia. The collision will be slow, taking millions of years to complete, but the results will be dramatic. The ocean between Australia and Asia will gradually close. Islands that currently exist in the gap, places like Indonesia and Papua New Guinea, will be crushed and folded as the two continents come together. New mountain ranges will form, possibly rivaling the Himalayas in height. Earthquakes and volcanic eruptions will become more frequent in the collision zone as the crust buckles and melts. And then, eventually, Australia and Asia will be one landmass. Species that evolved separately for millions of years will be able to migrate between the continents. Ocean currents will be redirected. Climate patterns will shift. It will be a new chapter in Earth's history, brought about by the simple, steady movement of a continent across the planet's surface. But Australia isn't the only continent on the move. Let's talk about Africa. Africa is doing something truly remarkable. It's splitting apart. Right now, along the eastern edge of Africa, from Ethiopia down through Kenya and into Tanzania, there's a massive crack in the Earth's crust called the East African Rift. This rift is a place where the African continent is literally tearing itself in two. The process started about 22 million years ago, and it's still going strong. The African tectonic plate is splitting into two smaller plates. The Nubian plate, which includes most of Africa, and the Somali plate, which includes the Horn of Africa and the eastern edge of the continent. These two plates are moving apart from each other at a rate of about 6 to 7 millimeters per year. That's slower than Australia's northward movement, but it's still significant over geological time. Right now, the East African Rift is a series of valleys, some of them thousands of meters deep, dotted with volcanoes and hot springs. It's an incredibly active geological zone, with earthquakes and volcanic eruptions happening regularly. One of the most dramatic examples occurred in 2005, when a massive crack opened up in the Ethiopian desert. In just a few days, the ground split apart, creating a fissure 60 kilometers long and several meters wide. It was as if the Earth had suddenly decided to take a giant step in its slow dance of continental separation. The East African Rift is actually made up of two branches. The Eastern Rift runs through Ethiopia and Kenya, and it's the more active of the two. This is where we see the most dramatic volcanic activity, with mountains like Kilimanjaro and Mount Kenya rising along its length. These volcanic peaks formed as magma pushed up through cracks in the thinning crust, building layer upon layer of cooled lava over millions of years. Even now, volcanoes like Oldoinyo Lengai in Tanzania continue to erupt, adding new material to the landscape. The Western Rift runs through Uganda, Rwanda, Burundi, and Tanzania, passing through some of the deepest and largest lakes in the world. Lake Tanganyika, Lake Malawi, Lake Albert. These long, narrow lakes formed in the valleys created by the rifting process. As the crust pulls apart, it creates low points where water collects. These rift lakes are incredibly deep, some reaching more than 1,400 meters in depth. They're like windows into the Earth's interior, places where the thinning crust has allowed water to fill the gap left by continental separation. The landscape of the East African Rift is otherworldly. In some places, you can see steep valley walls rising thousands of meters on either side of flat valley floors. In other places, volcanic cones dot the horizon, some still smoking from recent eruptions. Hot springs bubble up from underground, heated by magma chambers lying just beneath the surface. The ground itself is unstable, with frequent earthquakes reminding residents that they're living on one of the most geologically active places on Earth. But perhaps most remarkable are the visible cracks themselves. In Kenya, there are places where you can see the ground literally splitting apart. Cracks meters wide run across farmland and roads, forcing communities to adapt to a landscape that's changing beneath their feet. In some areas, these cracks have damaged buildings and infrastructure, a very real reminder that continental movement, while slow, is also powerful and unstoppable. Scientists study the East African Rift intensely, because it's one of the few places on Earth where we can see continental rifting happening in real time. Most of the time, rifting occurs under the ocean, hidden from view. But here, in East Africa, it's happening on land, where we can observe it, measure it, and learn from it. Geologists have set up monitoring stations throughout the region, using GPS receivers, seismometers, and other instruments to track every tiny movement, every earthquake, every volcanic eruption. What they've learned is fascinating. The rift is opening at different rates in different places. In some areas, the rate is as slow as 2 millimeters per year. In other areas, particularly in the Afar region of Ethiopia, it's opening much faster, up to 16 millimeters per year. The variation tells us that the forces driving the rift aren't uniform. There are hotspots beneath the crust, places where plumes of hot mantle material rise up and push the plates apart more aggressively. There are also variations in the strength of the crust itself, with some areas resisting the rifting forces more than others. One of the most intriguing questions is what will happen to the Afar Triangle, a low-lying desert region in Ethiopia where three rift systems meet. This is where the East African Rift joins the Red Sea Rift and the Gulf of Aden Rift, creating a junction point between three separating plates. The Afar region is already below sea level in some places, and as the rifting continues, it's sinking lower. Scientists predict that this will be one of the first areas to be flooded by the ocean when the rift finally opens completely. When that happens, perhaps 5 to 10 million years from now, the Red Sea and the Gulf of Aden will connect to the East African Rift, and seawater will pour in, creating a new ocean where there's currently dry land. The Afar Triangle will become an ocean basin. The shores of this new sea will be the coastlines of a separated Africa, with the Somali plate drifting away to the east and the Nubian plate remaining in the west. It's a process that's happened many times before in Earth's history. The Red Sea itself formed this way, when the Arabian Peninsula split away from Africa about 30 million years ago. At first, it was just a rift valley, similar to what we see in East Africa today. But over millions of years, the rift widened, the crust thinned, and eventually seawater flooded in. Now the Red Sea is a narrow ocean, still widening as the Arabian and African plates continue to move apart. The East African Rift is following the same pattern. It's just in an earlier stage of the process. In geological terms, it's still a young rift, just getting started. But give it time, tens of millions of years, and it will mature into a full ocean basin, with spreading ridges generating new oceanic crust, and the separated continents moving farther and farther apart. Where is this leading? If the process continues, if the African plate keeps splitting apart, then in about 5 to 10 million years, the eastern edge of Africa will separate completely from the rest of the continent. The Indian Ocean will flood into the Rift Valley, creating a new ocean basin. Countries that are now landlocked, like Uganda and Zambia, might one day have their own coastlines. A new island continent, made up of Somalia, parts of Ethiopia, Kenya, and Tanzania, will drift away into the Indian Ocean, leaving a wider, changed Africa behind. Think about what this means for the people and animals living in East Africa. The landscapes they know, the ecosystems they depend on, will be completely transformed. Species that currently range across East Africa will find themselves divided by a growing ocean. New coastlines will create new habitats. The climate will change as ocean currents are redirected. It will be a complete transformation of the region, driven by forces deep beneath the surface. Of course, geological predictions are uncertain. The process might speed up, slow down, or even stop. The Earth's internal forces are complex and not fully understood. But the evidence suggests that Africa is in the process of splitting, and that process will continue for millions of years to come. We're witnessing the birth of a new ocean, right here, right now, on the continent where humanity itself was born. Meanwhile, other plates are moving in their own directions. The Pacific Plate, the largest tectonic plate on Earth, is sliding northwest at about 8 to 9 centimeters per year. This movement creates the famous Ring of Fire, a zone of intense volcanic and earthquake activity that circles the Pacific Ocean. As the Pacific plate grinds against other plates, it creates subduction zones where one plate slides beneath another, generating earthquakes and feeding magma to volcanoes. The North American plate is moving slowly westward, away from Europe. This movement is opening up the Atlantic Ocean, making it wider by about 2.5 centimeters each year. If you could watch in fast-forward time-lapse, you'd see the Atlantic gradually expanding, pushing North America and Europe farther and farther apart. South America is moving westward as well. Grinding against the Nazca Plate and creating the Andes Mountains, the longest mountain range in the world. Every earthquake that shakes Chile or Peru is a reminder that these plates are still in motion, still pushing against each other, still building mountains. Even Europe is on the move. The Eurasian plate is slowly rotating and shifting, which is why the Mediterranean region is so prone to earthquakes. Greece, Italy, Turkey. These places sit on the boundary between different plates, feeling the effects of continental movement in very real, sometimes tragic ways. All of this movement, all of these shifting plates, are part of the same global system. The Earth's crust is like a giant, three-dimensional jigsaw puzzle, except the pieces are always moving, always changing shape, always interacting with each other in complex ways. Some plates are colliding, creating mountains. Some are pulling apart, creating rift valleys and new ocean floor. Some are sliding past each other, creating earthquakes. It's a dynamic, ever-changing system, driven by heat from deep within the planet. Now you might be wondering how we know all of this. How can scientists tell that continents are moving when the movement is so slow? The answer lies in some very clever technology and careful observation. One of the most important tools is something called GPS, or Global Positioning System. You probably use GPS to navigate while driving, or to find your location on your phone. But GPS is also a scientific tool. By placing very precise GPS receivers at various locations around the world and measuring their positions over time, scientists can detect tiny movements in the Earth's crust. They can literally watch the continents move, millimeter by millimeter, year by year. These measurements have confirmed everything we know about plate tectonics. They've shown that Australia really is moving north at 7 centimeters per year. They've shown that North America and Europe really are moving apart. They've measured the expansion of the East African Rift. GPS has turned continental movement from a theory into an observed fact, something we can measure and track in real time. The precision of modern GPS is truly remarkable. These systems can detect movements as small as a fraction of a millimeter. Scientists have placed GPS receivers on stable bedrock in hundreds of locations around the world, and these receivers constantly communicate with satellites orbiting overhead. By comparing the position of each receiver over time, scientists can see exactly how much it has moved, in what direction, and at what speed. The data from these GPS networks has revealed fascinating details about plate motion. For example, scientists have discovered that plates don't always move at constant speeds. Sometimes they speed up or slow down in response to changes in the forces acting on them. They've also found that the boundaries between plates aren't always clean lines. There are transition zones where the crust is being stretched or compressed in complex ways, creating networks of small faults and fractures. One of the most interesting discoveries came from studying the GPS data from Japan. Scientists noticed that in the years leading up to the devastating earthquake of 2011, the Pacific plate appeared to be moving slightly faster than usual as it pushed beneath the Japanese islands. This accelerated movement was building up stress in the crust, stress that was eventually released in the form of that massive earthquake and tsunami. While scientists can't yet predict earthquakes with certainty, GPS data is giving them new insights into how stress builds up in the Earth's crust and where future earthquakes might occur. GPS technology has also helped us understand more subtle aspects of plate tectonics. For instance, scientists have discovered that tectonic plates can actually bend and flex slightly as they move. In some places, the weight of volcanic islands on a plate can cause the plate to sag downward, creating a shallow depression in the seafloor. In other places, plates can bulge upward, where hot plumes of mantle material push against them from below. These deformations are tiny, just a few centimeters or meters, but GPS can measure them, helping us understand how plates respond to the forces acting on them. Another tool is satellite imagery. Satellites equipped with special instruments can measure tiny changes in the shape of the Earth's surface. They can detect when one side of a fault line moves relative to the other. They can see the slow uplift of mountain ranges. They can track the expansion of rift valleys. From orbit, these satellites watch the Earth changing, documenting the slow dance of continents in precise detail. One particularly powerful technique is called interferometric synthetic aperture radar, or INSAR. This technology uses radar beams bounced off the Earth's surface from satellites. By comparing radar images taken at different times, scientists can create detailed maps showing how the ground has moved, even if the movement is just a few centimeters. This technique has been used to study the gradual sinking of land in areas where groundwater is being extracted, the slow expansion of volcanic magma chambers before eruptions, and the subtle movements of ground along fault lines between earthquakes. INSAR has revealed movements that would have been impossible to detect even a few decades ago. In California, scientists use it to monitor the San Andreas Fault, watching as the Pacific and North American plates slowly grind past each other. In Iceland, they use it to track the expansion of the Mid-Atlantic Ridge as it pushes the island apart. In the Andes Mountains, they use it to study the compression and uplift caused by the Nazca Plate sliding beneath South America. Scientists also use seismology, the study of earthquakes, to understand what's happening beneath the surface. Every earthquake sends waves through the Earth, and by studying these waves, scientists can create a kind of three-dimensional map of the planet's interior. They can see where tectonic plates meet. They can identify subduction zones, where one plate slides beneath another. They can track the movement of hot plumes of rock rising from deep in the mantle. All of this information helps build a complete picture of how and why the continents move. Seismic waves come in different types. Some, called P waves, can travel through both solid rock and liquid magma. Others, called S waves, can only travel through solid rock. By studying which types of waves arrive at different locations around the world after an earthquake, scientists can determine what kinds of material they pass through. This has allowed them to map the internal structure of the Earth, showing where there's solid rock, where there's partially melted rock, and where there are completely molten regions. One of the most significant discoveries from seismology is the identification of subduction zones. These are places where one tectonic plate is sliding beneath another, plunging down into the mantle. Subduction zones generate some of the most powerful earthquakes on Earth, and they're also the places where old oceanic crust is recycled back into the mantle. By studying the earthquakes that occur in subduction zones, scientists have been able to map the geometry of descending plates, showing how they bend and break as they sink into the hot mantle rock. Seismology has also revealed the existence of mantle plumes, columns of hot rock rising from deep within the Earth. These plumes create hotspots at the surface, places of unusual volcanic activity that aren't related to plate boundaries. The Hawaiian Islands, for example, sit above a mantle plume. As the Pacific Plate moves northwestward over this stationary hotspot, new volcanic islands form, creating a chain of islands that gets progressively older the farther you go from the current hotspot location. This chain of islands is like a record of the Pacific Plate's movement, showing both its direction and speed over millions of years. Perhaps one of the most fascinating lines of evidence comes from the ocean floor itself. When magma rises at mid-ocean ridges and cools to form new rock, it preserves a record of Earth's magnetic field at that moment in time. Every few 100,000 years, Earth's magnetic field flips. North becomes south, south becomes north. And each time this happens, the newly formed rock on the ocean floor records the direction of the magnetic field like a frozen compass. Scientists have found stripes of rock with alternating magnetic orientations on either side of mid-ocean ridges. These magnetic stripes are like a tape recording of Earth's history, showing how the ocean floor has spread over millions of years. They provide direct evidence that new crust is being created at the ridges, and that the ocean floor is moving away from those ridges over time. It's one of the most elegant and convincing pieces of evidence for plate tectonics. The pattern of these magnetic stripes is remarkably symmetrical. On either side of a mid-ocean ridge, you see the same pattern of stripes, mirrored across the ridge. This symmetry makes sense if new crust is forming at the center and spreading outward in both directions. It's like watching a slow-motion zipper unzipping, with new material being added to both sides simultaneously. By measuring the width of these magnetic stripes and knowing when each magnetic reversal occurred, scientists can calculate exactly how fast the ocean floor has been spreading. Different ridges spread at different rates. The East Pacific rise spreads relatively quickly, at about 15 centimeters per year. The Mid-Atlantic ridge spreads more slowly, at about 2.5 centimeters per year. These differences tell us about variations in the forces driving plate tectonics in different parts of the world. The magnetic stripe patterns also allow scientists to reconstruct the past positions of continents with remarkable precision. By measuring the age and position of oceanic crust on either side of a mid-ocean ridge, they can work backward in time, closing the ocean basin and bringing the continents back together. This is how we know with such confidence where the continents were millions of years ago, and how Pangaea was arranged before it broke apart. All of this evidence, from GPS measurements to magnetic stripes, from earthquake data to satellite imagery, tells the same story. The continents are moving. The Earth's surface is in constant, slow motion. And we can measure it, track it, and predict where it's going. It's a remarkable achievement of modern science, this ability to see and understand processes that operate on such vast scales of time and space. We've transformed what was once speculation into proven fact, turning the invisible into the visible through careful observation and clever technology. But what drives this movement? What's the engine that powers plate tectonics? The answer lies deep inside the Earth, in the mantle, a layer of hot rock that makes up most of our planet's volume. The mantle is not quite solid and not quite liquid. At the high temperatures and pressures deep inside the Earth, rock can flow very slowly, like thick honey or cold molasses. This flowing rock is driven by heat from Earth's core, which is itself heated by the radioactive decay of elements like uranium and thorium. As these elements break down, they release energy, and that energy heats the rock around them. Hot rock is less dense than cool rock, so it rises toward the surface. As it rises, it cools down, becomes denser, and eventually sinks back down toward the core. This creates giant circular currents in the mantle, convection currents that move at a speed of just a few centimeters per year. But that's enough. These currents push and pull on the tectonic plates above them, dragging them along like leaves floating on a slow-moving stream. Think of it like a giant planetary-scale lava lamp. Hot material rises, spreads out, cools and sinks, creating a circular motion. Except instead of colorful wax, we're talking about thousands of kilometers of solid rock flowing like a very thick fluid over millions of years. It's hard to imagine, but that's the scale we're dealing with. The Earth operates on timescales so long and forces so subtle that they're almost beyond human comprehension. Yet they shape the world we live on. The mantle itself is divided into different layers, each with its own properties. The upper mantle, which extends from the base of the crust down to about 410 kilometers, is where most of the convection that drives plate tectonics occurs. This is where the rock is hot enough to flow, but still solid enough to transmit seismic waves. Below this is the transition zone, where increased pressure causes minerals to transform into denser crystal structures. And below that is the lower mantle, extending down to the core mantle boundary at a depth of about 2,900 kilometers. The lower mantle is even hotter than the upper mantle, with temperatures reaching several thousand degrees Celsius. At these temperatures and pressures, rock behaves in ways that are hard to imagine. It can flow, but incredibly slowly, taking millions of years to complete a single convection cycle. The lower mantle is thought to contain massive, slow-moving currents that extend from the core all the way to the base of the upper mantle, driving the entire plate tectonic system from below. Scientists have discovered that these deep mantle currents aren't uniform. There are regions where hot rock is rising faster, creating what are called superplumes. These superplumes appear as huge columns of hot material rising from near the core mantle boundary. When they reach the base of the lithosphere, they can cause dramatic effects at the surface, including extensive volcanic activity, uplift of the land, and changes in plate motion. One such superplume is thought to exist beneath Africa. This African superswell may be responsible for the unusually high elevation of large parts of southern and eastern Africa. And it's also thought to be one of the main driving forces behind the East African Rift. The hot mantle material rising beneath Africa is pushing the lithosphere upward and pulling it apart, creating the conditions for continental rifting. Another superplume exists beneath the Pacific Ocean. This Pacific superswell is responsible for many of the volcanic island chains and submarine volcanoes scattered across the Pacific Basin. As the Pacific Plate moves over this region of hot, upwelling mantle material, it creates volcanic hotspots that punch through the crust, forming islands like Hawaii, Tahiti, and the Cook Islands. Where the hot mantle rock rises to the surface, we get spreading, zones like the Mid-Atlantic Ridge, where new crust is created. The rising hot rock doesn't just push the plates apart, it also melts slightly as it reaches lower pressures near the surface, creating magma that wells up through the crack between the separating plates. This magma cools and solidifies, forming new oceanic crust that becomes part of the moving plates. The process of seafloor spreading is continuous. At mid-ocean ridges around the world, new crust is being created right now, this very moment. The ridges themselves are underwater mountain ranges, often 2 to 3 kilometers high, running for thousands of kilometers across the ocean floor. They're dotted with volcanic vents, hot springs, and hydrothermal systems, where superheated water, rich in minerals, pours out of the seafloor. These hydrothermal vents support unique ecosystems, communities of life that don't depend on sunlight at all. Instead, they rely on chemicals dissolved in the hot water, using chemosynthesis rather than photosynthesis as their energy source. These vent communities, with their giant tube worms, eyeless shrimp, and specialized bacteria, show us that life can thrive in the most unexpected places, powered by the heat from Earth's interior. Where the cool rock sinks back down, we get subduction zones, places where one tectonic plate slides beneath another, pulling old crust back down into the mantle to be melted and recycled. Subduction zones are among the most dramatic features of plate tectonics. They're marked by deep ocean trenches, the deepest parts of the ocean floor, where the descending plate bends downward and begins its journey back into the mantle. The Mariana Trench in the Western Pacific, the deepest point in the world's oceans, is a subduction zone. Here, the Pacific plate is diving beneath the smaller Philippine plate, creating a trench more than 11 kilometers deep. At these depths, the pressure is more than 1,000 times atmospheric pressure at sea level. Only a handful of people have ever visited the bottom of the Mariana Trench, making it one of the least explored places on Earth. As an oceanic plate descends into the mantle at a subduction zone, it carries water and sediments with it. This water, locked into minerals in the descending plate, is released as the plate heats up at depth. The released water lowers the melting point of the surrounding mantle rock, causing it to melt and form magma. This magma is less dense than the surrounding rock, so it rises upward, eventually erupting at the surface to form volcanoes. This is why subduction zones are associated with lines of volcanoes, often called volcanic arcs. The volcanoes of Japan, the Andes Mountains of South America, the Cascade Range of the Pacific Northwest, and the islands of Indonesia all formed this way, above subduction zones where descending plates generate magma that feeds volcanic eruptions at the surface. These volcanoes can be incredibly powerful. The eruption of Mount Pinatubo in the Philippines in 1991, the eruption of Mount St. Helens in Washington state in 1980, and the massive eruption of Krakatoa in Indonesia in 1883 all occurred at subduction zone volcanoes. These eruptions not only shape the local landscape, but can also affect global climate by ejecting huge amounts of ash and gas into the stratosphere. And where plates slide past each other horizontally, we get transform boundaries. Places like the San Andreas Fault in California, where the movement creates powerful earthquakes. Transform boundaries don't create or destroy crust. Instead, they allow plates to slide past each other, accommodating differences in the speed and direction of plate motion. The San Andreas Fault is perhaps the most famous transform boundary. It marks the boundary between the Pacific Plate, which is moving northwest, and the North American Plate, which is moving southeast. The two plates grind past each other at a rate of about 5 centimeters per year. Most of the time, friction keeps them locked together. But stress builds up over years and decades until finally the rocks break and the plates lurch forward, releasing the built-up energy in the form of an earthquake. All of this, the rising and sinking of mantle rock, the spreading of ocean floors, the collision of continents, the creation and destruction of crust, is part of one interconnected system. We call it the tectonic cycle, and it's been operating for billions of years, constantly reshaping the surface of our planet. It's a system driven by heat from within, powered by radioactive decay in the Earth's interior, and manifested at the surface as the slow, inexorable movement of continents across the face of the globe. Now let's look to the future. If the continents are moving now, where are they going? What will Earth look like millions of years from now? Scientists have created computer models to predict the future of continental movement. These models take into account the current direction and speed of each tectonic plate, the forces driving them, and the patterns we've observed from past continental movements. While the predictions get less certain the farther into the future we go, scientists can make some educated guesses about what might happen over the next few 100 million years. One of the most widely discussed predictions is the formation of a new supercontinent. Just as Pangaea formed from the collision of earlier continents, and just as Pangaea broke apart to form today's continents, scientists believe that the continents will eventually come back together again to form another supercontinent. This hypothetical future supercontinent has been given several names. One of the most popular is Pangaea Proxima, which means next Pangaea in Latin. Another name is Pangaea Ultima, meaning last Pangaea, though scientists now prefer Proxima because it doesn't imply that it will be the last supercontinent ever to form. According to the Pangaea Proxima model, here's what might happen. Over the next 50 to 100 million years, the Atlantic Ocean will stop expanding and begin to shrink. New subduction zones will form along its edges, pulling the ocean floor down into the mantle. As the Atlantic closes, the Americas will start moving back toward Europe and Africa. Meanwhile, Australia will continue its northward journey until it crashes into Southeast Asia, probably within the next 20 to 50 million years. Africa will continue to move northward as well, closing up the Mediterranean Sea and creating new mountain ranges where it collides with Europe. About 250 million years from now, all of these movements will culminate in the formation of Pangaea Proxima. The Americas will have collided with Europe and Africa. Australia will be wedged against Asia. Antarctica, which is currently sitting at the South Pole, will have drifted north to join the other landmasses. All of Earth's continents will once again be connected into a single, massive supercontinent. This new supercontinent will be shaped roughly like a ring, with a small ocean trapped in the middle where the Mediterranean and Indian Oceans used to be. The rest of Earth will be covered by a single enormous ocean, a new panthalassa encircling the supercontinent. The geography will be completely different from today. The maps we know will be meaningless. Countries, borders, coastlines, all of it will have been erased and rewritten by the slow movement of tectonic plates. What will life be like on Pangaea Proxima? Climate models suggest it won't be pleasant, at least not by our current standards. The interior of the supercontinent, far from any ocean, will become a vast desert. Without ocean currents to moderate temperatures, the center of Pangaea Proxima could experience extreme heat, with temperatures regularly exceeding 40 degrees Celsius and possibly reaching as high as 50 or 60 degrees. Only the polar regions and coastal areas will be temperate enough to support complex life. Scientists have even suggested that these extreme conditions could lead to a mass extinction event. Many species might not be able to survive the harsh climate of the supercontinent's interior. Mammals, which regulate their body temperature through sweating and breathing, might struggle to survive in the intense heat. Some scientists have speculated that if humans are still around 250 million years from now, they might have to find ways to adapt to these conditions, or perhaps live in the more habitable polar regions. Of course, all of this is speculation. Predicting what will happen 250 million years in the future is extremely difficult. The forces driving plate tectonics could change. New convection patterns could develop in the mantle. Unexpected geological events could alter the path of continents. Scientists are the first to admit that their models of future supercontinents are educated guesses, not certainties. There are other proposed future supercontinents besides Pangaea Proxima. One alternative is called Amasia. In this model, the Atlantic Ocean continues to expand while the Pacific Ocean, which is already shrinking, closes completely. This would bring the Americas into collision with Asia, creating a supercontinent centered around the North Pole. Another proposal, called Novopangaea, suggests that the continents will rotate around the planet and come together on the opposite side of the Earth from Pangaea's location. Which of these, if any, will actually happen? We don't know. We won't be around to see it. But what we do know is that the continents will continue to move, continue to shift, continue their slow dance across the surface of the planet. The Earth is not static, it's dynamic, ever-changing, constantly reshaping itself on timescales far beyond human comprehension. Let's pause for a moment and think about what all of this means. We live on a planet that is, quite literally, alive with motion. Not in the biological sense, of course, but in a geological sense. The ground beneath our feet is part of a massive, planet-sized conveyor belt system, driven by heat from the core, powered by forces we can barely perceive. Every mountain range is a frozen moment in a collision between continents. Every ocean basin is a place where the Earth has pulled itself apart. Every earthquake is a reminder that the plates are still moving, still grinding against each other, still reshaping the world. We might not feel it in our daily lives, but the evidence is everywhere if we know where to look. The matching coastlines of Africa and South America, the identical fossils found on continents separated by thousands of kilometers of ocean, the slow growth of the Himalayas, the volcanic activity along the Ring of Fire, the earthquakes in California and Japan and Indonesia, the expanding Atlantic Ocean, the splitting of East Africa. All of it tells the same story. The Earth is in motion, the continents are on a journey, and we, all of us, are passengers on this incredible ride. Think about the timescales involved. Pangaea formed 335 million years ago. It began to break apart 200 million years ago. The continents reached their current positions over the last 65 million years, and they won't stop here. In another 250 million years, they might come together again to form Pangaea Proxima. These numbers are so large, they're hard to grasp. Hundreds of millions of years. Time periods so long that entire species can evolve, flourish, and go extinct many times over, while the continents slowly drift across the globe. To us, with our lifespans of 70 or 80 or perhaps 100 years, the Earth seems permanent. Mountains seem eternal. Oceans seem unchangeable. But in geological time, mountains are temporary. Oceans open and close like doors. Continents drift like clouds across a sky, merging and separating in an endless cycle. And yet, this slow movement has shaped everything about our world. It's determined where mountains rise and where plains spread. It's controlled the flow of ocean currents, which in turn affects climate patterns around the globe. It's separated populations of plants and animals, allowing different species to evolve in isolation. It's created the diverse landscapes we see today, from the peaks of the Andes to the valleys of East Africa, from the islands of Indonesia to the vast plains of Siberia. Continental movement has even influenced human history in ways we're only beginning to understand. The formation of mountain ranges created natural barriers between cultures, shaping the development of languages, technologies, and societies. The opening of oceans allowed species to spread to new lands, and later allowed humans to explore and settle distant continents. The collision of India with Asia created the Himalayas, which influenced the development of civilizations on both sides of those mountains, affecting everything from trade routes to religious traditions to agricultural practices. Climate patterns shaped by continental positions have influenced where humans could thrive and where deserts form. The monsoon patterns of Asia, which bring life-giving rains to billions of people, are partly caused by the position and shape of the Asian landmass. The Gulf Stream, which keeps Western Europe warmer than it would otherwise be, exists because of the position of the Americas and the shape of the Atlantic Ocean basin. These ocean currents, these climate patterns, these geographic features that seem so permanent, are all products of continental movement. Even the minerals we extract from the earth, the resources that power our modern civilization, are distributed the way they are because of plate tectonics. When continents collide, they create mountain ranges, and in the intense heat and pressure of these collisions, rare minerals become concentrated in ways that make them economically viable to mine. When volcanic activity occurs at subduction zones, it brings minerals from deep in the mantle to the surface, creating ore deposits of copper, gold, and other valuable metals. The breakup of Pangaea, for instance, created rift zones where volcanic activity was intense. These ancient rift zones are now some of the richest mining regions in the world. The diamonds found in South Africa formed deep in the mantle and were brought to the surface by volcanic eruptions associated with the early stages of Pangaea's breakup. The copper mines of Chile, the gold deposits of Nevada, the iron ore fields of Australia, all of these exist where they do because of the movements of tectonic plates over hundreds of millions of years. We are, in very real ways, products of plate tectonics. The world we inhabit, the landscapes we call home, the climates we've adapted to, the resources we depend on, all of it has been shaped by the slow dance of continents across the face of the earth. Our species evolved in the East African Rift, in a landscape being torn apart by continental forces. Our ancestors spread across the world, following coastlines and crossing land bridges that existed because of the particular positions of continents at that time. Our entire history as a species has unfolded against the backdrop of moving continents, even though we never realized it until very recently. There's something almost poetic about it, isn't there? We rush through our lives, worried about deadlines and appointments, while beneath our feet, the continents are taking the longest, slowest journey imaginable. We measure time in seconds and minutes and hours. The Earth measures time in millions and hundreds of millions of years. We see change happening all around us, in technology, in politics, in culture. The Earth sees change too, but on a scale so vast we can barely comprehend it. We live our entire lives in a geological instant. The ground beneath us feels solid, permanent, unchanging. But if we could step back and watch Earth over millions of years, we'd see it as the dynamic, living system it truly is. We'd see continents dancing across the globe like clouds across a sky, colliding and separating, creating mountains and oceans, constantly reshaping themselves in an endless cycle driven by the heat from the planet's core. And yet, in a strange way, we're connected to that deep time. The atoms in our bodies were forged in stars billions of years ago. The oxygen we breathe was released by ancient organisms over millions of years. The ground we stand on has traveled thousands of kilometers from where it was when dinosaurs walked the earth. We are made of old matter, living on an old planet, which is itself still young and changing in the context of cosmic time. The rock beneath your feet might have been at the bottom of an ancient ocean millions of years ago. It might have been part of a mountain range that has since eroded away. It might have been buried deep in the earth and then uplifted to the surface. The calcium in your bones might once have been part of a coral reef in a tropical sea that no longer exists. The iron in your blood might have been forged in a supernova explosion billions of years before Earth even formed. We're all made of stardust, riding on continents of recycled ocean floor, breathing air that's been processed through billions of years of life, living on a planet that's in constant, slow-motion transformation. Perhaps that's the most humbling realization. We tend to think of ourselves as the center of things, the pinnacle of creation, the most important beings on the planet. But plate tectonics reminds us that we're just one small part of a much larger story. The Earth was doing this dance long before we arrived, and it will continue long after we're gone. Continents were colliding, separating when the first life crawled out of the oceans. They were moving when the dinosaurs ruled. They were shifting when early humans first stood upright. And they'll still be moving millions of years from now, when whatever comes after us looks back and tries to understand the world they inherited. There's a kind of comfort in that, actually. In a world that often feels chaotic and unpredictable, it's nice to know that some things operate on their own schedule, undisturbed by our worries and plans. The continents don't care about stock markets or elections or any of the things that occupy our daily thoughts. They just keep moving, steadily, patiently, following the deep currents of the Earth's mantle. They're on their own journey, their own timeline, and nothing we do can speed them up or slow them down. And maybe there's a lesson in that. Maybe we could learn something from the continents, not to rush, not to force things, to trust in the slow, steady processes that shape the world. To understand that real change, meaningful change, often happens gradually, almost imperceptibly, building up over time until one day you look back and realize how far you've come. Mountains aren't built in a day. They're built over millions of years, one tiny increment at a time. Oceans don't open overnight. They spread gradually, year after year, century after century, until what was once land becomes sea. In our human lives, we're often impatient. We want results now. We want to see change immediately. But perhaps the Earth has something to teach us about patience, about the power of small, consistent movements over long periods of time. A continent moving at 7 centimeters per year doesn't seem like much, but give it 50 million years and it will have traveled 3,500 kilometers. That's the distance from New York to London. That's the width of an ocean. Small movements, sustained over long periods, can accomplish extraordinary things. The continents move without us realizing it, but they do move. Slowly, patiently, inexorably. And in that movement, there's something beautiful, something profound. A reminder that the Earth is not a finished work, not a static backdrop to human history, but a living, breathing planet, constantly changing, constantly renewing itself, constantly creating new landscapes and new possibilities. Every earthquake, every volcanic eruption, every mountain range slowly rising or slowly eroding is part of this grand planetary process. We're witnessing it, living through it, whether we realize it or not. So the next time you look at a map, remember that what you're seeing is just a snapshot, a single frame in a movie that's been running for billions of years. Those continents aren't fixed in place. They're travelers, adventurers, wanderers on an incredibly long journey. They've been to places you can't imagine, and they're going to places we can only dream about. And we're along for the ride, whether we realize it or not. Each continent has its own story, its own journey through time and space. North America has drifted from the tropics to its current temperate position. Africa has rotated and moved northward, closing ancient oceans and opening new ones. Antarctica once sat near the equator, covered in forests, before drifting to the South Pole where it became encased in ice. Every piece of land has a history written in its rocks, a tale of ancient collisions and separations, of ocean basins opening and closing, of mountains rising and eroding away. And these stories continue. Right now, as you rest and listen, North America is moving a tiny bit farther from Europe. The Atlantic is getting wider. In California, the Pacific Plate is sliding past the North American Plate along the San Andreas Fault, carrying Los Angeles slowly towards San Francisco. In the Himalayas, India continues to push into Asia, raising the mountains a few millimeters higher. In East Africa, the continent is pulling apart, widening the Rift Valley by a few millimeters. These movements are happening right now, at this very moment, invisible but real, powered by the heat flowing from Earth's core. Think about the sheer constancy of it. Day after day, year after year, century after century, millennium after millennium, the continents keep moving. Through ice ages and warm periods, through mass extinctions and evolutionary radiations, through the rise and fall of countless species, the continents have kept moving. They moved while trilobites crawled across ancient seafloors. They moved while dinosaurs roamed Pangaea. They moved while our ancestors learned to walk upright. They're moving right now while you listen to these words, and they'll still be moving long after everything we know has changed beyond recognition. As we come to the end of our journey tonight, I hope you found something here that resonates with you. Maybe it's the sheer scale of geological time. Maybe it's the idea that change, even very slow change, is powerful and inevitable. Maybe it's just the wonder of knowing that the ground beneath you is on a journey, carrying you along on an adventure you'll never fully see but are always a part of. Perhaps it's the realization that patience and persistence, the qualities embodied by these moving continents, can accomplish things that seem impossible when viewed from the perspective of a single lifetime. Wherever you are right now, as you listen to these words, know that you're moving, not just through space as the Earth orbits the Sun, or as the solar system moves through the galaxy, but also across the surface of the planet itself. You're riding on a tectonic plate that's been moving for hundreds of millions of years and will continue to move for hundreds of millions more. You're part of the Earth's story, a tiny chapter in an incredibly long book. And when you wake up tomorrow morning and step outside, maybe you'll look at the ground a little differently. Maybe you'll remember that what seems solid and permanent is actually just a passenger on a slow-moving journey. Maybe you'll see mountains not as eternal monuments, but as temporary sculptures created by colliding plates and slowly eroding away. Maybe you'll look at oceans not as permanent features, but as spaces that opened when continents drifted apart, and that might close again someday when they drift back together. The world is always changing, always moving, always becoming something new. And so are we. Just like the continents, we're on a journey. We might not always know where we're going, but we're moving nonetheless, shaped by forces we don't always understand, heading toward futures we can't quite predict. But here, now, in this moment, we can pause. We can breathe. We can let go of our need to rush and simply be present. The continents aren't in a hurry. The Earth has all the time in the world. And maybe, just for tonight, so do we. Thank you for joining me on this gentle exploration. Thank you for your time, your attention, your curiosity. Whether you're still awake or drifting off to sleep, I hope you've enjoyed this journey through deep time and slow motion. I hope you felt the wonder of living on a planet that's always changing, always moving, always creating something new. From all of us here at the Sleepy Library, may your rest be peaceful and your dreams be full of slowly drifting continents and quietly rising mountains. You have done enough for today. Your thoughts can settle now, like continents finding their place. Close your eyes, rest deeply, and know that even in stillness, you're part of something vast and beautiful. Let the earth carry you gently through the night. Sleep well.